This is now the third lecture in which we're taking a close look at the first second in the life of the universe. It's a time characterized by enormous temperatures and densities and rapid expansion. And last lecture, we went back to a microsecond, when the furnace was fully alive, in the sense that all the particles of the Standard Model were present in full abundance. And as time passed and expansion cooled the furnace, there was a cascade effect in which particles annihilated with antiparticles in a sequence, first the heavier ones and then the lighter ones. And finally, we arrived at the minute-old universe, with more or less today's composition, mainly photons and a few protons, helium nuclei, and electrons. Well, in this lecture, I want to visit the pre-microsecond universe. I know this sounds a bit absurd, but by now you should be familiar with the enormous speed with which nature thinks. So there'll be plenty to keep us occupied for the next 30 minutes looking at just that first microsecond. In fact, there are three primary themes I want to focus on. First, I want to look at whether there are any more particle thresholds at even higher energy associated with new particles we've not yet come across. Second, I want to look at how the laws of physics, and in particular the four forces, subtly change as the temperature drops. And finally, I want to explore why that carnage of matter-antimatter annihilation somehow managed to leave behind a small amount of matter to make you and me and everything else around us. So let's start by regaining our bearings using the time-temperature graph that shows how the universe cools and thins as it expands. The version of this graph we're using last lecture is just this portion in the lower right. Remember, we have neutrino decoupling at 1 second, quark confinement at 10 microseconds, and before that we have the quark-gluon plasma. So I've really extended the graph to earlier times. Look how the time axis goes in steps of 10 to the 5, all the way back beyond 10 to the minus 40 seconds. The scale factor also spans a huge range. You can see the size of today's visible universe at these earlier times. 10 light years, solar system size, Earth size, football field size, and at 10 to the minus 40 seconds, it was just a millimeter across, the size of the ball in a ballpoint pen. And of course, at these extremely early times, the temperatures and densities were outrageously high. Now, it won't come as a big surprise to learn that we're moving into conditions shrouded in genuine uncertainty and ignorance. So let me just qualify that now. Remember, today's biggest particle accelerators can achieve energies of about 10 TeV of energy, which gets us back to about 10 to the minus 14 seconds, basically the entire rectangle from last lecture. These accelerators, of course, have helped build the Standard Model of particle physics, the laws of physics that occur within this box. And as far as we can tell, it's an extremely good and well-tested theory. So one might crudely identify this region with well-known physics and this with known physics, while before that is uncertain physics. Or stated slightly differently, most cosmologists are very confident back to 1 second, pretty confident back to about a microsecond, optimistic back to the limits of this box at about 10 to the minus 14 seconds, and they have their fingers crossed before that. Now, while we're on the topic of uncertainty, I should mention that everyone agrees there is a boundary of absolute ignorance around 10 to the minus 43 seconds. It's also called the Planck time. This is where Einstein's general relativity breaks down and gravity inevitably takes on a quantum form. And as you may know, we currently have no quantum theory of gravity. It's a notoriously difficult thing to develop. So until that's done, this time and these conditions, if they ever occurred, remain fundamentally unknown. So with these various warnings, let's take a deep breath and step off into this rather unknown terrain. What happens when we go to ever earlier times with ever higher densities and ever higher temperatures? Well, the Standard Model has no heavier particles. So the quark-gluon plasma just gets denser and denser and hotter. Now, this may seem a bit unreasonable. How can stuff be denser than an atomic nucleus? Isn't that the densest thing there is? Actually, the answer is no, and here's why. Remember how much space there is inside atoms? A nucleus at the centre of an atom is like a fly at the centre of a football field. Remove that space from atoms and you can fit the entire human population inside a sugar cube. Now that's nuclear density, 100 million tons per cubic centimetre. But the same story also applies to protons. For reasons I don't have time for just now, we think that the real size of quarks is a mind-boggling 10 to the 20 times smaller than a proton. So 3 quarks zooming around inside a proton is like 3 viruses zooming around inside the solar system. There's plenty of room to cram the quarks more tightly together. Now, if the Standard Model is the whole story, then not much happens to the left of that rectangle. Across 20 powers of 10 in time, it gets 10 powers of 10 hotter and 40 powers of 10 more dense. That's an enormous tract of time. As much in an exponential sense as from a millisecond to 10 billion years. So if really nothing happens, then it's earned its name, the particle desert. There are no interesting features on the landscape. But in truth, we know the Standard Model is incomplete, and several of the possible extensions beyond the Standard Model do suggest interesting things occur, and perhaps the desert isn't quite so featureless after all. So one of these extensions to the Standard Model is called supersymmetry. This theory suggests that in the very early universe, the laws of physics were identical for the 2 great kinds of particles, the fermions and the bosons that we met in lecture 27, the matter particles and the force-carrying particles. Now, if this is true, then in the early universe, there should be a second set of much heavier particles. Each particle of the Standard Model should have a superparticle partner of the opposite kind. So although these particles haven't yet been discovered, physicists have already named them. I suppose it's a bit like choosing a baby's name before it's born. So the superpartners of the Standard Model fermions, the electron, neutrino and quark, are bosons called the selectron, sneutrino and squark. You just add an S prefix. And the superpartner particles to the Standard Model bosons, the photon, W and Z and gluon, are fermions called the photino, the wino, the xeno and the gluino. You just add an eno postfix. Now, from our perspective, the most important fact about all these superparticles is that the heaviest superparticles are unstable and they decay to the lightest one, which is itself stable. It isn't yet known which of them would likely to be stable. Possibly it's the photino, or maybe an odd mix of several in a state called a neutralino. But either way, we have a new particle to consider which survives into today's universe. Now, I hope you can see why this is fabulous news for astronomy, because we need a particle outside the Standard Model to explain dark matter. We know there's 6 times more matter out there than there are protons, neutrons and electrons. And we know it can't be neutrinos, because they're too lightweight. They move too fast to gather around galaxies and clusters. So we need a heavy, stable particle that's not one of the standard model particles. Maybe the lightest supersymmetric particle solves the mystery. Back to our time-temperature diagram, there are reasons to place the superpartner particles around here, and perhaps the lightest one arrives here. Ultimately, these particles emerge with all the rest as dark matter, providing, as we saw in earlier lectures, the scaffolding on which stars and galaxies and the galaxy web later form. So this is a wonderful story, and it may soon be tested directly because the newest accelerator at CERN has sufficiently high energy that many physicists feel it will be able to create the lightest supersymmetric particles. So finally, the primary constituent of the universe's matter would be brought into our experimental arena, where it could be studied in detail. Now let's turn to our second major theme for this lecture, the emergence of the four forces. But really, I want to place this in a larger framework and talk about the emergence of the laws of physics. This is surely a deep subject. Why does nature behave the way it does? Now, to a physicist, nature's laws arise from what are called invariance principles or symmetry principles. It's a slightly tricky concept, but it boils down to asking whether an interaction between particles would or would not be affected by changing some aspect of the situation. For example, if we move the interaction from one location to another, or if we change the particles to antiparticles, is the interaction affected at all, or does it stay the same? If the changes don't affect the interaction in any way, we say the interaction is invariant under that change. And there's a rather unexpected consequence of that invariance. Something else, some other quality, is conserved during the interaction. For example, the fact that interactions aren't affected by their location, whether it's over here or over here, leads directly to the conservation of momentum. The fact that interactions aren't affected by when they occur, whether they happened yesterday or today, leads directly to the conservation of energy. Now, this link between the changed quantity and the conserved quantity isn't at all obvious, and it was first famously worked out by the great German mathematician Emmy Noether in the 1920s. Now, it turns out there are many of these paired quantities, and while some are classical, like location with momentum or time with energy, others are quantum mechanical, and they involve some more abstract qualities down in the quantum world. But the bottom line is that these invariance principles and their conservation laws, they really are the laws of physics. Or stated the other way around, the laws of physics are nothing more than the consequence of whether nature does or doesn't ignore certain things. Now, as it happens, exactly what nature does or doesn't ignore depends on the energy of the interaction. In general, at very high energies, nature ignores almost everything, and the interactions are, in some sense, more perfect, more global and all-encompassing. This, of course, was the situation in the very early universe, when the energy of all interactions was exceedingly high. The laws were more perfect, more unified. But as time passed and the universe cooled, some of these invariance principles no longer operated, or they operated with less precision. Physicists say the symmetries were broken, and as a result, the laws of physics changed, and so the way particles interacted also changed. This is why particle accelerators are so important. They're able to take us back to a time when the laws of physics were different, and they help us track how these laws evolved into their current form. So with that preamble, let's now look at the forces of nature and see how they've changed. In today's old, cold universe, we learn, even in grade school, that there are 4 forces: gravity, weak, electromagnetism, and strong. Let's just quickly review these and put them into the context of the Standard Model. So here are the particles of the Standard Model. Over on the left, we have the bosons, the force-carrying particles. What does this mean exactly? Here's a little animation of a quantum mechanical view of how forces act between particles. A boson particle hops between 2 particles, and the energy and momentum that it carries alters the particles' trajectories. So a force has acted. So let's briefly go through these forces. Gravity is the force that holds you to the Earth and planets in their orbits. It acts between all particles, is carried by gravitons, and is extremely weak. The weak force only operates deep inside particles and causes them to change, as in radioactive decay. It also acts between all particles and is carried by the W and Z bosons, and, as its name suggests, it's relatively weak. The electromagnetic force drives lightning bolts from clouds to the ground and keeps electrons in orbit within atoms. It only acts between charged particles, it's carried by the photon, and is of intermediate strength. And finally, the strong force keeps quarks bound inside protons and neutrons and binds protons and neutrons together in atomic nuclei. It only acts between quarks and gluons, it's carried by gluons, and as its name suggests, it's the strongest of the forces, about 100 times stronger than the electric force. Now, in our day-to-day lives, we really don't experience the mighty power of these forces. The strong and weak forces are confined inside particles, and the electromagnetic force is enormously muted because positive and negative charges are so thoroughly intermixed. But to give you an idea, imagine I had 2 grains of sand, and I took all the electrons from one of them and put them into the other. And I took all the protons from the other and I put them into the first one. Then I held each grain at arm's length. There's an attractive force because opposites attract. But how big is that force? Can I hold them apart? The answer is very definitely no. There's 18 billion tons of force. I need 8 million space shuttles pulling on full throttle, pulling in opposite directions to keep these grains of sand apart. So these forces are stunningly powerful if you bring them up into our macroscopic world and fully expose them. So returning to the early universe, it turns out that in the exceedingly hot environment, the nature of these forces was different. For example, before 0.1 nanoseconds, the electromagnetic and weak forces were blended into a single force called the electroweak force. So prior to that time, there were really only 3 forces. So let's put this electroweak transition on our time-temperature diagram. Here it is at 1/10 of a nanosecond, when particles had about 100 GeV of energy. As the temperature dropped past this point, the weak symmetry condition was broken, and because of this, the electroweak force took on 2 different guises, the electromagnetic force and the weak force. Notice that the transition is well within the region studied by particle accelerators, and so this whole transition is actually very well understood. Now, during this transition, another extremely important change occurred. If we go back to our diagram of the Standard Model, you'll remember this odd particle called the Higgs boson. Well, one of the consequences of the electroweak symmetry breaking was that this particle, or more accurately, the field associated with this particle, changed. And from then on, all the other particles interacted with this field and as a result gained the mass that we now measure them to have. So before 0.1 nanoseconds, none of the particles had any mass. They were all, in a sense, like photons. So without this change, all the particles that make up our world would always be moving at the speed of light. And as the universe expanded, they would have been redshifted away to almost nothing, just like the microwave background photons. So this electroweak transition with its changing Higgs field is really had some very crucial consequences. Well, now we have two of the four forces united. Can we unify three? There are several reasons to think that the answer is yes, but the best evidence is the way in which the strengths of the three forces changes with increasing energy. They converge on a single value. This diagram shows the predictions of the Standard Model, which are backed up by measurements, for how the strengths of the forces change from low energy on the left to high energy on the right. The three forces seem to be converging towards the same strength. The strong force gets weaker, while the electromagnetic force gets stronger. The convergence is even better if we include supersymmetry in the calculations. They seem to cross at a single point up at the incredibly high energy of 10 to the 16 GeV. Okay, let's go back to our time temperature diagram. This energy occurs way back at 10 to the minus 36 seconds, or 10 to the 28 degrees. At this extraordinary temperature, it is thought that the electroweak and strong forces become tied together in what's called the grand unification theory, or gut force. Now, you don't need me to tell you that this is an enormous extrapolation beyond familiar conditions. But this kind of approach has worked before. Newton extrapolated from the falling apple to the Earth orbiting the Sun, about as big a jump. But clearly, we're in the realm of uncertain physics here. Actually, there's quite a bit of indirect evidence for the gut force. In addition to the crossing of the four strengths, grand unification also explains why electrons and protons have exactly equal but opposite charges. And it also gives an exactly correct prediction for the ratio of the W and Z masses. But perhaps the most interesting prediction of the gut theory is that the proton should itself be slightly unstable, so that in time all atomic nuclei will undergo radioactive decay. Fortunately, we don't have to worry about this. The current estimate for the proton lifetime is around 10 to the 36 years. That's a billion times the age of the universe. Now, there are, in fact, experiments to look for this proton decay. See, if you gather 10 to the 36 protons, that's about 1 million tons of matter, then on average, one proton will decay per year. And perhaps you can detect this. Actually, that's the principle behind this 50,000-ton chamber of water surrounded by very sensitive light detectors located under a mountain in Japan. Now, so far, no proton decays have been detected, but the search continues, and there are plans to upgrade this to a 1 million-ton chamber. Now let's look at the third theme for this lecture: how the universe narrowly escaped total matter-antimatter annihilation. So from last lecture, remember, at very high temperatures, collisions create particle-antiparticle pairs. So the composition of the early universe before, say, a microsecond was an equal mix of matter, antimatter, and photons. Now, in today's old cold universe, the laws of physics always require a particle to be created along with its antiparticle. No process can favour the generation of matter over antimatter. They are true equals. So if this were true in the early universe, there would be exactly equal amounts of matter and antimatter. So the matter-antimatter annihilation would be totally complete. Now, since the annihilation ultimately makes photons, we'd have a universe with just photons, just light, nothing else. Well, here we are, made of matter, so clearly this can't be the whole story. Now, one possibility, of course, is that the universe really is balanced in matter-antimatter, but while the Milky Way galaxy is made of matter, perhaps the Andromeda galaxy is made of antimatter. You could never tell just by looking, because matter and antimatter behave identically. It's only when the matter and antimatter mix that you know they're different, because they annihilate to make gamma rays. Well, it turns out that although intergalactic space is pretty empty, it isn't that empty, and we would easily see the gamma ray radiation coming from the boundaries where matter and antimatter mingled. So we're really quite sure we live in a matter universe with no antimatter left over from the Big Bang. So there must have been an asymmetry in the matter-antimatter production in the early universe, so that after the period of annihilation, there was a bit of matter left over. Now, an important question is, how great was that asymmetry? For every proton that survived, how many annihilated? It's actually easy to figure out this because each annihilation makes a photon, and these photons become the microwave background. So the ratio of annihilations to surviving protons is the same as the ratio of the number of microwave background photons to cosmic protons. And we know what this number is. It's about 1 billion. So there's your matter-antimatter asymmetry. 1 part in 1 billion excess of matter over antimatter. It's a very, very slight excess. So here's the situation. In the early universe, for every billion antimatter particles, in blue, we have 1,000,000,001 matter particles, in red. After the annihilation is over, that one extra matter particle is left standing and is surrounded by the 2 billion photons, in yellow, made in the annihilation. This is really a remarkable situation for several reasons. First, every proton and electron in your body has survived a game of Russian roulette with 1 billion bullets and 1 blank. They are incredibly lucky to be here. Secondly, all the matter that you see around you in the Earth and stars and galaxies is only 1 billionth of what was made in the Big Bang. It was an enormously more fertile event than appears at first sight. And thirdly, if there hadn't been this very slight matter asymmetry, the annihilation would have been complete, and the universe would contain only light, which might have been more beautiful, but there would have been no one to appreciate it. So let's look at how this narrow escape happened. The idea goes back to 1967, when the famous Russian physicist Andrei Sakharov realized that generating a matter-antimatter asymmetry needs 3 rather general conditions. Here they are. 1, quarks and leptons must be able to interconvert. 2, matter and antimatter reactions must differ in some way. And 3, these processes must occur in a non-equilibrium state, which happens during periods of rapid change. Now, if we look to the standard model for these mechanisms, you won't find any. The physics responsible for generating the matter asymmetry is beyond the standard model and is currently basically unknown. Of course, there are several theories which tend to focus on one of the 2 major transitions, the gut transition and the electroweak transition. But, along with supersymmetry, grand unification, quantum gravity, and inflation, matter asymmetry is just one more feature of the early universe that must await future breakthroughs before we can say that we really understand it. Now, I want to end this lecture on a slightly more reflective note. We've been talking about how, in that first second, all the particles were created and the laws of physics shifted and changed. But what determines those laws? How does nature know to generate a quark-antiquark pair and not two quarks, for example? Where does the knowledge reside to do all these things just the right way? Currently, our best guess is that the knowledge is somehow embedded in the vacuum. Remember, by pumping energy into the vacuum, it creates all the particles in ways that obey these laws. So in some sense, the knowledge to do that is located at every point in space. Everything rests on this extraordinary entity. It's the vacuum that is nature's ultimate bedrock. It gives life to the universe and it informs it how to behave.